Okay. Now, we will again start with the we ended with the two parameters V max, that is equal to K 2 into E 0, and we have K m, that is equal to what we have seen, that K m is equal to K minus 1 plus K 2 divided by K 1. Okay. And K m has a concentration unit, okay, concentration unit. Now, if you plot the initial velocity, if you suppose take various substrate concentrations, okay, keeping the enzyme concentration constant, suppose you have taken a constant concentration of an enzyme and you add different substrate concentration S 1, S 2, S 3 and determine the initial velocity for each of these reactions. Okay. You can determine, and these initial velocities will be different for the different values of S. Okay. Now, if you have many points like that, S 3 then S 4, that means you are slowly suppose increasing the substrate concentration, okay, and you determine the initial velocity and then you plot the initial velocity with substrate concentration. So, what will happen, that you will see that the velocity initially, as you increase the substrate, the velocity increases, okay, because you have, suppose the enzymes have there are many enzyme molecules which have these active sites. So, initially the active sites are, number of active sites are more than what is your substrate molecules. So, all substrate molecules will not fill up the active sites. Okay. The more active sites you fill, the more rate you will get. Okay. So, as you increase the substrate, then greater number of active sites starts filling up. So, the rate also increased, but this will happen up to a certain point. At some point what will happen, because your enzyme concentration is constant, all the active sites will be filled by the substrate molecules. So, beyond that, if you increase the substrate concentration, you will not get any rate enhancement. So, so the nature of the graph will be like this, that it increases and finally slowly coming to a constant value. Okay. And so, suppose I extend it like this, a constant value. So, this is the maximum velocity that you can get with a particular enzyme concentration, maximum velocity V max. Okay. So, this is your V max. So, now you know this is what is called the saturation. At this point, the enzyme is saturated with the substrate, like your saturated solution, that you add sodium chloride to water. If your water content is fixed, then after certain point the sodium chloride will not dissolve any further. It is very similar to that. So, that is why this is called saturation of the enzyme. This is your V max. That V max depends on what? Depends on your initial enzyme concentration. If you vary the initial enzyme concentration, your value of V max will also change. Okay. Now, we have earlier told that K m is nothing but equal to the substrate concentration required to reach half of V max, substrate concentration to reach half of V max. So, what you do? Once you know the V max, now you see what is the half of V max. So, this is half of V max. So, now you draw a line here and then see what is the value in the x axis. So, that gives you what is this value of S is equal to what is K m. Okay. So, that is there. Now, that is how you determine the K m. Now, what is the significance of K m? K m can be defined in two ways. One is K m is basically the ratio of these rate constants. On the other hand, you can define it as the substrate concentration required to reach half of the V max. Okay. Both are correct, but both are important, but let us analyze this part first. What happens in enzyme catalysis is usually that as you add the substrate, the enzyme and the substrate, they after few minutes quickly adopt an equilibrium stage. That means that ES complex, the steady state complex is reached very quickly, and that is because K 1 and K minus 1 are much higher than the value of your K 2. K 2 is the rate constant for the decomposition of ES into the product, which is actually much less as compared to the these values K minus 1 and the rate constants for the formation of the ES complex and the rate constant for the breakdown of the ES complex. So, these are much higher than K 2. So, that means you can now summarize it, you can simplify it a little, that K m is approximately equal to K minus 1 by K 1. What is that? K minus 1 by K 1? K minus 1 by K 1 is your reaction is nothing but E plus S going to ES, and that is going to E plus P. This is the reaction scheme. So, this is K 1 and this is K minus 1. So, usually K 1 by K minus 1 is the equilibrium constant if we consider from left to right. Now, here it is K minus 1 divided by K 1, that means it is the dissociation constant now. Earlier K 1 by K minus 1 was basically association. Now, K minus 1 by K 1 is the dissociation constant of the ES complex. So, that means K m is also roughly equal to the dissociation constant of the ES complex. What does it mean then? Is higher K m better for enzyme efficiency or lower K m better for enzyme efficiency? Now, one thing is clear, that more the concentration of this ES, the higher will be the, because K 2 is the formation of the rate of formation of the product is basically K 2 into ES. So, if you have high concentration of ES, if you can maintain higher concentration of ES in the system, then you will have higher turnover of ES into the product. Okay. Now, if the dissociation of ES to E plus S is very high, that means the association is low, that means your ES concentration is low, that means your rate of the reaction will ultimately will be low. So, the enzyme will be less efficient. And on the other hand, if K m is low, that means your dissociation is low and your association is high. If that be the case, that means your turnover to the product will be ultimately higher. So, for an enzyme reaction, K m is very important. Lower K m means higher binding or tighter binding, higher binding constant. Okay. So, K m, you see the same parameter can be defined in several ways, that K m is the dissociation constant of the ES complex, or K m is the substrate concentration to reach half of the Vmax. Okay. Okay, now, how do you really prove that the Michaelis-Menten equation is correct? As I said, the earlier graph was not a linear graph, it took a shape like this. So, it is very difficult to really plot a graph which is not linear. What actually we try to do always is to have a linear graph. So, we convert the equation in such a fashion that the ultimately when we plot the x and y, then it gives a linear, it gives a straight line, and that is much better, because straight lines you can confidently draw if your points are within a straight line. If they stray away a little bit, like in the earlier case, it is really difficult to draw this, experimentally it is difficult. So, always there is an attempt to represent an equation in such a form that ultimately when we plot x and y, it gives a linear graph, and that is what is done by, from the same equation If you take 1 by V 0, so that becomes 1 by V max, that means it is S by S V max, so S and S crosses out. So, this is 1 by V max and this becomes K m by V max into 1 by S. This is what is called this gives you a double reciprocal plot, because what you are plotting now, if you plot 1 by V 0 versus 1 by S now, what will happen? Now, that will be linear, because this is now y equal to m x plus c, that form. So, now you get a straight line, and this straight line, what is the value here? Value of the x axis here, that will be equal to minus 1 by K m, because here what? Here your 1 by V 0 is becoming 0, that means you put 0 equal to 1 by V max plus K m by V max into 1 by S. So, if you solve this, you will get that S equal to, because your V max will cancel out. So, if you solve this, S becomes equal to minus 1 by K m. Okay. So, that means this intercept is minus 1 by K m. The minus value comes because it is on the other side of the x axis. Okay. So, experimentally, how to determine K m? That you take the enzyme concentration constant and add the substrates in different concentrations in different test tubes and measure the initial rate, and then you plot 1 by V 0, that means 1 by initial rate and the 1 by against the each substrate concentration, but take a double reciprocal. This is what is called a double reciprocal plot, or it is also known as the scientists who did this, showed the way how to determine or how to convert Michaelis-Menten equation into a linear form. So, that is also called Lineweaver-Burk plot. Okay. And this intercept is basically 1 by V max. Here you put 1 by S equal to 0. So, that will give the y axis, y is equal to 1 by V max, and the slope is nothing but this K m by V max. So, by doing these type of experiments, means determining the initial velocity at different substrate concentration at a particular enzyme concentration, you can determine this V max and the K m. These are the two extremely important parameters for the equation. Now, factors affecting enzyme catalyzed reaction. One, as I said, enzyme concentration. The more enzyme you have, the more the greater will be the rate of the reaction. Substrate concentration. It depends on the substrate concentration, but you have to be careful. After beyond a particular substrate concentration, you cannot increase the rate of the reaction, because you will reach the saturation point. That is at that point the velocity is what is called V max. Temperature also plays a part, because the enzyme works when it is in the native state. If you apply some energy, some heat energy to the enzyme, so there will be some unfolding will take place, or if you apply some salts into the solution, some unfolding will take place, or if you change the pH, that also disturbs the conformation of the enzyme. So, all these things will dictate, or we can say that the enzyme efficiency will be dependent on these parameters: temperature, pH, presence of hydrogen bond disrupting agent like urea. Urea is very simple molecule CONH2, but that has got hydrogen bond donor and acceptor, and that is a very good molecule to disrupt the hydrogen bonds that are present in a protein. So, if you add urea, the protein slowly denatures, the hydrogen bonds get breakage, and also sometimes or on many occasions there are other small molecules which look like the substrate, but they are not actually substrate for the enzyme, but they go and sit and cover the or do not make available the active site. So, if you do that, then the then some active sites will be lost by the presence of those small molecules which are called inhibitors. So, inhibitors are small molecules basically that slows down the enzyme kinetics. So, these are the different parameters. Now, one more point. So, Km, when we say that factors affecting enzyme catalyzed reactions, that means these are the ones which affect the Km and the Vmax. These are the ones which ultimately, how do you know that the enzyme efficiency has gone down? So, you have to measure the Km and the Vmax, then you will know that yes, something is happening, there is a slowing down of the rate. So, now the one interesting point is that if you the question is Km is dependent on temperature, that is okay. It is dependent on pH, that is also fine. It is suppose you do not add any other organic molecule. So, no inhibitor is there. So, it is dependent on these, dependent on pH, it depends on the ionic strength of the solution, that is also fine. But the question now is, does Km depend on the initial enzyme concentration or not? Because Km can be defined as the concentration to reach half of the Vmax. Okay. So, if we increase the enzyme concentration, suppose I have a particular enzyme concentration E1, where this is the graph suppose. So, this is the Vmax, then this is the Vmax, and half Vmax is this. This is half Vmax. So, that means the Km is this. Now, if we increase the enzyme concentration, so what will happen? Definitely the Vmax will increase, because you have more number of active sites. So, you can have more substrates now. So, the value of Vmax will also increase. So, Vmax will definitely increase, but interestingly what will happen, suppose the Vmax now increases and goes to that point. Suppose this is the area, this is now the new Vmax, but if you calculate half of Vmax, you will see that it will cut at the same, it will give the same value of Km. So, again I repeat, Vmax will change as you change the enzyme concentration, but the concentration to reach half of the Vmax still remains the same. Okay. The concentration needed to reach the half of Vmax remains the same. So, Km is independent of the enzyme concentration. Okay. Now, if we want to really go into the molecular more details, that how enzymes catalyze a reaction, because what we have seen earlier is really not at the molecular level we are thinking. We have a very broad perspective, a cartoon type diagram, and then an equation, and then solve the equation, find the parameters. But the more intricate details is how the enzymes catalyze the reaction, what really happens there, because we have seen that substrate goes, binds, but something happens to the substrate. How the enzyme is able to do that, carry on that. Okay. Now, we will just show here the mechanism of one protease which we have already encountered, and that is called chymotrypsin. Remember what is chymotrypsin? Chymotrypsin is an enzyme which recognizes amino acids or which cleaves peptide bonds from the carboxy end when there is aromatic amino acids present in the system, in the peptide bond. Okay. So, that means, if you have a peptide bond like this CO NH, and this is the peptide and this is the peptide. So, here there must be some aromatic group, and that is what is needed. So, the peptide bond that is broken is this one. So, that is what is chymotrypsin. Now, the question is, in order to hydrolyze a peptide bond, what is needed? That you have to have water, and that ultimately has to come here and break it. But That does not happen. It is not so simple that if you take a protein and dissolve it in water, the protein never hydrolyzes. Okay. And that is very good, because if proteins are hydrolyzed, then our body will be so fragile, all the proteins will be hydrolyzed. Okay. So, that does not happen, fortunately. To have this hydrolysis by water to happen, what you need is some other nucleophile which can attack this carbonyl and then ultimately break this bond, and then the nucleophile is released later on by water. So, that is what is the mechanism of the protease class of molecules. Now, there are different proteases. Proteases, again I repeat, they are the enzymes which hydrolyzes the peptide bond. Okay. There are the different types of protease depending on this nucleophile. I said the enzyme must be having some nucleophile which is attacking which is a much better nucleophile than water. Water is not a good nucleophile. What is good nucleophile is OH minus, but in the biological system at biological pH 7 or 7.2, you do not have this alkalinity which is needed to hydrolyze the peptide bond. Okay. Instead, the enzyme provides the nucleophile. So, internally it attacks, and then this breaks, and then finally water comes and releases the X again. So, that this goes out, and then another molecule comes in. Now, depending on the nature of X, you have different types of proteases. One is called serine protease. Serine protease, where X is basically an amino acid containing X means X is OH, because we are talking about serine. What is serine? OH, like this, okay, NH and CO. This is what is serine. So, serine OH is the nucleophile, and then if serine OH is the nucleophile by which that hydrolyzes the peptide bond, then those class of enzymes are called serine proteases. Similarly, we have SH here, instead of OH you can have SH, and those are called cysteine proteases, because SH comes from only cysteine. A third one where you do not have internal nucleophile like this, but what the enzyme provides is a metal ion, because you know that many of the addition to the carbonyl compounds are assisted by acids like Lewis acids. There are many reactions which are assisted by Lewis acids which activates the carbonyl. Okay. Similarly, Lewis acids are nothing but you have a metal halide, say aluminum chloride, okay, or boron trifluoride. What happens because of the vacancy, because of the not the octet structure, it has not fulfilled the octet structure. So, these are got very good Lewis acid character, BF3 or AlCl3. Now, in case of enzyme hydrolysis, this also can be achieved by simple metal ions, like suppose M plus, which is a zinc, say. So, oxygen will chelate to the zinc. As soon as oxygen chelates to the zinc, what happens? The electrophilicity of this carbon increases. Okay. So, now in presence of metal ions, you do not need any other nucleophile other than the actual nucleophile, that what you require, that is water. So, in presence of metal, water can come, attack this is assisted by the metal ion. Now, who is holding this metal ion? The enzyme is holding the metal ion. So, metal ion becomes the cofactor in that case. So, metal ion activates the carbonyl, water comes and breaks the amide bond. So, direct. These are called metalloproteases. So, we have serine protease, metalloprotease, and then cysteine protease, but there is another category that is called the aspartyl protease. What is aspartyl protease? Where again that is the catalyzed, directly water comes and attacks the carbonyl. Okay. Again I come to the, again going back to what I have said, that when you have a bond, if you want to break a bond involving a carbonyl, I have two options. One is either use a powerful nucleophile to attack the electrophilic carbonyl carbon, break the carbon nitrogen bond, or I can activate the oxygen through some processes like metal ion, and then water comes and attacks. Now, if instead of metal ions, if this is a proton, because you know many of the, again the carbonyl reactions, addition of DNP, hydrazine, all these are catalyzed by acids, because the acid protonates the carbonyl and the nucleophile is the hydrazine or a phenylhydrazine, semicarbazide, all these can attack very easily. Now, who will provide this acid? Again the enzyme, because the enzyme can have aspartic acid where there is H plus. So, the aspartic acid proton can protonate a carbonyl of an amide bond, and then water can come and hydrolyze the amide. So, these are the 4 classes. In one classes you have direct attack by water, which is assisted by chelation of the carbonyl oxygen either to metals in case of metalloproteases, and in case of aspartyl protease, the aspartic acid provides the proton source to protonate the carbonyl and then allow the water to attack the carbonyl, and so the carbon nitrogen bond is broken. This is one side, and on the other side you have a good nucleophile present in the enzyme, and that comes, and as it is a good nucleophile, so that attacks the carbonyl and this amide bond leaves. But in that case you see there is a covalent bond formation between the enzyme and the carbonyl carbon. Okay. So, the enzyme is momentarily stuck with the remaining part of the protein, and that is called the acyl enzyme complex. So, the acyl enzyme complex will next be hydrolyzed, then water will come and break the acyl enzyme complex, and you get your nucleophile back, and the result is that you have done the hydrolysis of the peptide bond. Okay. In the next session, what we will start from here, but we will raise the question. The question is that what is a good nucleophile in enzymes, because enzymes do not have nucleophiles like cyanide, a good nucleophile like iodide, that is not there, or hydroxide, that is also not there. So, what is the good nucleophile in case of enzyme? We said that there is a class which is serine protease, and chymotrypsin in fact is a serine protease type enzyme. Serine is nothing but an amino acid containing an alcoholic OH. The question is, alcoholic OH, is it sufficiently nucleophilic to hydrolyze a peptide bond? In order to answer that, what you need to do? So, let us check. I take a peptide and add some methanol, because that also have alcoholic OH, but nothing happens. Okay. If you add ethanol, nothing happens. So, no alcohol can hydrolyze the peptide bond. So, the biggest challenge that was posed at that time, when it was discovered that serine protease utilizes serine as the nucleophile and hydrolyze the peptide bond, then the big question came that how is it possible that serine can attack a carbonyl and break a carbon nitrogen bond. Okay. So, we will stop here and we will start from this, how the serine, that means there is again a question of activation of the nucleophile. The power of the nucleophile has to increase, so that it can attack the carbonyl. Okay. So, we will start from there, that how the serine is activated, and ultimately that leads to the attack of the carbonyl. Okay. Thank you.